atomic model. Niels Bohr suggested a model for the hydrogen atom that predicted the existence of line spectra. This model used Planck's and Einstein's idea about quantized energy. There are 4 postulates in Bohr's atomic model. The first one, the electron moves around the nucleus in a fixed circular orbit. So in the middle is the nucleus, and this is the circular orbit. The nearest one is n equal to 1. We call it principal energy, or the first shell, n equal to 1. And the second one, n equal to 2. The third one, the third orbit, n equal to 3. Second postulate, electron at certain energy level has certain amount of energy, or the energy of electron is quantized. The energy of electron can be represented in this formula, En equal to negative RH 1 over n squared. RH is Rydberg constant. So the value of n, which is principal quantum number or energy level or stationary state or the number of particular orbit, can be 1, 2, 3 until infinity. The value here is negative because when you have E infinity, when the n is infinity, it means that the electron is already removed from the orbit of the atom. So when n is equal to infinity, E infinity is 0. So all other energy, when n is below infinity, the other energy must be negative. That's why the equation is negative. So this is the shell or the orbit, n equal to 1, the nearest to the nucleus. So you can substitute E1 equal to negative RH 1 over n squared. Your n is 1, so 1 over 1 squared. So RH is 2.18 times 10 to the power of negative 18. So your E1 is negative 2.18 times 10 to the power of negative 18. So this is n equal to 4, the principal quantum number, or the shell, the fourth shell, n equal to 4. It has the energy of E4 equal to negative RH 1 over n squared. Your n is 4, so 1 over 4 squared. So this is the value for E4. The third postulate, an electron moves in an allowed energy state will not absorb or radiate energy. No change of energy while electron moves within an orbit. So when you have an orbit and the electron moves around that particular orbit, there will be no absorb or radiate energy within that electron. The fourth postulate, energy is emitted or absorbed by an electron as it changes from one allowed energy state to another. So this means if the electron change the shell or change the orbit, energy will be emitted or absorbed. Before we're going on to the next section, you must know the definition of frequency and wavelength. Frequency is the number of waves undergoes per second. The unit is s-1 per second or hertz. Wavelength is the distance between identical points on successive waves. The unit can be nanometer, picometer, angstrom, meter, and etc. So, this is the equation for speed of light. The speed of light is equal to the frequency multiplied by the wavelength. The speed of light is fixed at 3 times 10 to the power of 8 meter per second. The change in energy of the electron is E2 minus E1, or E final, energy of final, minus energy of the initial. So that's the change of energy, final minus initial. So for example here, your final is E2 and E1 is the initial. So when you expand the change of energy, E final minus E initial, you will get this equation. The energy released or the energy absorbed can be calculated from the difference in energy between two energy levels using this equation. Remember that this one is initial and this one is final. RH is the Rydberg constant, and the change of energy can be equal to Planck constant times the frequency, or Planck constant times the speed of light over the wavelength. The change in energy is also known as energy of a photon. The energy emitted or absorbed is in a form of photons or electromagnetic radiation. Thus, it has specific energy and wavelength. So this is the equation to relate the energy emitted or absorbed with the frequency, speed of light, and the wavelength. Note that C is speed of light, H is the Planck constant in joules second, mu is frequency, lambda is the wavelength, photons, particles of light. The difference between ground state and excited state. The ground state is when n is equal to 1. It is the lowest allowed energy state and the most stable energy state. This is where the electron is the closest to the nucleus. Excited state is when n above 1, 2, 3 or infinity, higher energy than the ground state, so that's what we call excited state. The state or level an electron occupies after absorbing an amount of energy. And in excited state, the stability of the electrons decrease. This is the example of electron transition in hydrogen atom. In a hydrogen atom, you only have one electron. So, the electron falls from n equal to 4, the fourth orbit, to n equal to 1, the first orbit. So when electron falls from higher energy level to the lower energy level, the energy is released during the transition. So the change of energy is energy final minus energy initial, where n initial equal to 4 and final equal to 1. You can use this equation to calculate the energy change, or if you want to find out the frequency, you can use this equation. So if the electron transit from the first orbit to the fourth orbit, from lower energy level to the higher energy level, we say the energy is absorbed. One mole of electrons drop from the fourth energy level to the third energy level. So note that from high energy level to low energy level, so the energy is released or emitted. Calculate the energy of electron at the fourth energy level. Second, the energy of the photon emitted from the transition, and finally, the frequency of this photon. At the fourth energy level, you can just use the equation and then put the Ripert constant n equal to 4. So you'll get negative 1.36 times 10 to the power of negative 19 joule. Second, the change in energy. The initial orbit is n equal to 4. The final orbit is n equal to 3. So, use this equation and substitute the value and you get the change in energy. Finally, for the frequency, you have to use delta E equal to h nu. So you can find the frequency because you have the value of delta E and the Planck constant.